Hello, Calculus. Today we're going to be going over Handout 13, and we're going to be talking about linear approximations and differentials. And linear approximations is exactly what it sounds like. We're going to be using what we know of tangent lines and the derivative to approximate functions. And so, we look right here. The linear approximation technique uses tangent lines to approximate a function near certain points. That is, when we're near a particular point, we can use what we know of derivatives to approximate what the other values will be that are close to this function. And so this is useful when you need to reduce the number of computations. And let's say that you've got, some computer algorithm that has to do 1,000,000 computations in 10 seconds, or 1,000,000 iterations, should I say, in 10 seconds. Well, then it's useful to reduce the number of computations required per iteration. And so that's where different approximation techniques become very, very valuable. And so here is a fairly simple one, but there are much more complicated ones as well. And so let's go ahead and look at get a good geometric intuition of what's going on. Looking right here. The graph below shows a function with a tangent line at x equals 10. Right? And so if you zoom in right here, you notice that the tangent line, the values of the tangent line are pretty close to the values of the actual function. But as you get further away, this starts to differentiate, and we start to build more of an error. And if you look over here, you see the same function just zoomed in really close, and you can see 9, 10, 11 is right here, 12 and 13. At 11, you're still pretty close. At 12, you're starting to generate a little bit of an error right there. All right, so we're going to use the above graphs to fill in the table below. So we're going to find the approximate value based off the tangent line, and then look at the graph and try and get an actual value, and we're going to calculate the error. Okay. And before we do that, let's go ahead and fill in the y values here, 7, 8, and 9. All right, so the approximate value at 11, well, that's right here. And then the actual value is right here. They do appear to be right on top of each other. And, with our human eyes, I'd put that about 7.2 on each. So 7.2, 7.2, and we'll say the error is about 0 because our human eyes can't tell the difference. Although note that the error is a little bit more than 0. All right, so let's look at 12. At 12, the approximate value, we'll just call that at 8 just to make things simple. But note the actual value is up here. I'll call that at 8.2. And so that means we have an error here. Our value is 0.2 less than the actual value. And let's go ahead and just put a negative sign to indicate that. And then let's look at 13. The approximated value is here. Call that at 8.8. And then the actual value appears to be up here, and I just put that at 9.2. Leaving us with an error of 0.4. And note that, it's underneath, so the error is negative since it's less than the actual value. All right, and so let's look at the next question. Will you get a good approximate from the tangent line when x equals 20 if you require an error to be less than 5? And so of course, this would be, an absolute value of the error. And so let's look at this. So when x is 20, we're right here. And so the actual value appears to be north of 20, with the approximate value being south of 15. So that does definitely look to be more than an error of 5. And so will we get a good approximate value? And the answer is no. We will not get a good estimated value if we require an error to be less than 5. Okay, so for the next part, we're going to switch over to Desmos. And we're going to be looking at the graph of y equals cosine x. And we're going to be looking at values near pi over 2. And specifically, we want to know how far away from x equals pi over 2 can we go and still have an error that's less than 0.1. And here we have the graph y equals cosine x in red here, and then you can see that we've calculated our slope, which is m equals negative sine of x, where x is pi over 2. Plug that in, you get m equals negative 1. And here, if you work everything out, you will get a y-intercept here of pi over 2, and so that's how we get our tangent line right here. And so we want to know what's going on near this vicinity. How far away can we go and still have the accepted error? So let's go ahead and zoom in here. So we've zoomed into a point where you can see that, that the distance from here to here, that is 0.1, that is our error. And so we just kind of go on till we can see that whole distance here. It starts diverging. And so let's go ahead and see how far. See right here clearly, we're well above the error. It's a little bit far out, so we need to move in a little bit. So let's look right here. Let's see, do we have enough? 1, 2, 3, 4, not quite enough. Let's look at this one. 1, 2, 3, 4, 5 boxes. Looks like that's pretty close for what we're doing. So when we go up this line, we are right here, and at this point right here, that looks like that's at 2.44, and so that's as close as far as we can go on the right hand side, and still be within our error bars. And so, how far to the right can we go? We can go all the way out to 2.44. And we could do a similar process to see how far we could go to the left-hand side of the point pi over 2. All right, so let's get to this part right here. And here we're going to develop a more rigorous formula to determine a linear approximation. Alright, so we recall that the slope of a line is the same as the derivative of the line. And what is the derivative? But it's simply the limit as delta x approaches 0 for delta y divided by delta x, right? The slope is delta y over delta x, and for the derivative we're forcing delta x to be an infinitesimal. Okay, and so moving forward, we note that we have the 2 points. We've got A and F of A, because that's that point right there. And then we have the point X and F of X. Of course, we're assuming that X is close to A. And so now we come down to here. We have these approximate equal to, and so we look at the derivative, which again is the slope. F prime of A is about equal to delta y divided by delta x. Again, it's not exactly equal to that, it's only approximately equal to that. And recall that delta y, that's simply y2 minus y1 over x2 minus x1. Alright, and so again, f prime of a, that is our slope. And we're going to plug in our 2 points now so that we've got f of x minus f of a, that's our delta y, and that's going to be divided by x minus a. Alright, and so now we're going to solve this for f of x. Let's go ahead and keep this as an approximate. And so we got here f of x equals f of a plus f prime at a times x minus a. That's just a simple algebraic step. Go ahead and work it out on your own. Make sure this step makes sense to you. And so we call this our linear approximate. So we can go ahead and call this L of x, where L is our linear approximate. And we use a hard equal sign now. And say L of x, our linear approximation, equals f of a plus f prime of a times x minus a. And here it is, we have it, our formula for the linear approximation. And we'll put stars there for much fanfare. So let's use this linear approximation in this example here. We are looking at this equation right here, and we want to find a linear approximate of this equation near x equals negative 2. So the first thing we have to do is find the derivative of this function, which is simply 3x squared minus 2x. And then we plug in our value. We want to know f prime at a, which is the same as f prime at negative 2. And we plug that in to get the result. And we get 16 right there. And so this 16 is our slope of the line. Next, we need to know what is f of a, and that again is what is f of negative 2, and that's going to be, and you will get negative 9 right there. Alright, so let's go ahead and plug everything in. Let's get our linear approximation going. Our linear approximation is simply, first we're going to look at our f of a, so that's negative 9, plus our f prime at a, which was 16, and then simply x minus a. A was negative 2, so it's going to make this an x plus 2, since minus a negative is a positive. And there we go, that's it. That's our linear approximation formula. And again, this only works for values of x that are close to negative 2. And how close do you need to be? Depends on how much error you're willing to accept. Okay, so let's move on to the next one. So we're going to use the linear approximation to estimate the value of 1 over 4.002. So first thing we have to do is turn this into a function. And so we'll call this 1 over x, and we're going to call our a 4, since that's going to be the easy one to do. Alright, so what is f prime of x? Well, that's simply going to be negative 1 over x squared. And so what is f prime at a? Well, that's the same as f prime at 4. Plug that in, and we get negative 1 over 4 squared, which is negative 1 divided by 16. And for f of a, we simply just plug our value in, of 4, and so that's going to be 1 divided by 4. Okay, good. So we've got the makings of a good linear approximation. Let's go ahead and plug all this in. Our linear approximation formula, L of x, first we plug in 1 divided by 4, and then plus our f prime, which is negative 1 over 16, and this becomes x minus 4. So our next step is to figure out what's going on at 4.02. I'm sorry, 002. And so we simply plug that into our approximation formula. And so we get 1/4 minus 1 over 16 times 0.002. Alright, so it might be easier for us to convert everything into decimals at this point. So 1/4, that's 0.25. 1/16, that's 0.0625. And then times 0.002. And as we work it out, we get the following result. Oh, don't forget that parentheses. 0.25 minus 0.000125. Subtract this from 0.25 and we get 0.2498. Which, if you actually were to calculate 1 over 4.002, you find it is pretty much the same as this result right here. Alright, so we've seen how we can use this to approximate values, and this specific example might be a few extra steps than if we just calculate it normally, but you can see for more complicated calculations, this really could be a great time saver. So let's go ahead and take a look at this next one. Here we have a square root function, and so that's, the square root of x, that's x to 1/2, and so f prime of x is simply 1/2 x to the negative 1/2, since 1/2 minus 1 is negative 1/2. So let's plug what we have here. We're going to be using an a of 100, since that's going to be easy to work with. F of a equals f of 100. And what is the square root of 100? But it is 10. Okay. And so now let's look at f prime at a. What's f prime of 100? Note this is simply 1/2 times 1 divided by the square root of 100, which is going to be 10 to the negative 1. So this is simply 1 over 20. Okay. So let's go ahead and put everything together. Our linear approximation formula is f of a, which we found to be 10, plus f prime of a, which is 1 over 20, times x minus a, which in this case is 100. Alright, so let's go through this one. We got a 10 here, plus 1 over 20. 1 over 20 is the same as 0.05. And then 100.02 is, going to be 0.02 right there. And so calculating through everything, we've got 10 plus 0.05 times 0.02. 5 times 2 is going to be 10. And we have 1, 2, 3, 4 decimals, so you go back like so. Alright, and so adding these together simply gets us 10.001. Now, if you get your calculator out and calculate the square root of 100.02, you'll find that it is awfully close to the value that we found right here. Okay. All right, that's it. That's all we have for this handout. we went over a linear approximation technique and how to use this technique to approximate certain values using what we know of the derivative.